All right, let's look at question 7. This is from section 3.1. So we have a function p and we're given its second derivative. So first thing we want to do is to come up with a sign chart for the second derivative. But we don't have an interval that we're being told to work with. So we have to assume we're dealing with this second derivative for all real numbers. So I think a good place to start would be to figure out where this second derivative is equal to 0. So where is this expression, x plus 1, x minus 2 times e to the negative x, where is this equal to 0? So we have a product of 3 factors multiplied together equal to 0. The only way that can happen is if any one of those single factors is equal to 0. So let's set those equal to 0 individually. So I get x equals -1 for one of my zeros. X equals 2 for another. And then what happens when e to the x, e to the negative x, I set that equal to 0. So one thing I'll say is that if you raise a positive number to a power, the result has to be positive. So this is never going to equal 0. But let's say you don't notice that. Let's try to solve for x here. I can take the natural log of both sides, and I get the natural log of e to the negative x equals the natural log of 0. Natural log of e to the negative x, that simplifies to negative x equals natural log of 0. So x equals the negative natural log of 0. But natural log of 0 is undefined. So another way to, hopefully that's one of the reasonings I just gave you is convincing that that third factor has no 0. I have 2 places where the second derivative is equal to 0. That's -1 and +2. So now, one thing that's I want to make explicit here is after you've found where the second derivative is equal to 0, not only have you found those points, you've also shown that the second derivative is equal to 0 nowhere else. So that's why to make a sign chart, I just have to test a point in all my 3 like so I have found 2 points where I have zeros, which means effectively I've split up the real numbers into 3 different portions. So I need to find a test point for each one of these 3 portions. One test point where x is less than -1, one test point where x is bigger than 2, and one test point where x is in between -1 and 2. I like to choose 0 whenever I can because it's usually convenient to do so. But now I have to pick a point that's less than -1. I'll choose -2. And I'll choose a point that's bigger than 2. I'll choose 8. And the only reason I'm choosing 8 is because I'm trying to illustrate that you have a lot of freedom. You can kind of choose whatever you want. It does not have to be a number like all that close to, these boundary lines. So now that we have chosen some test points, let's evaluate the second derivative at each of them. So p double prime of -2 is equal to -2 plus 1 times -2 minus 2 times e to the -2. Or I should get -1 times -4, so 4 times e squared. That is a positive number. So that tells me everywhere to the left of x equals -1, I have a positive value for the second derivative. Now, what about p double prime of 0? That comes out to be 1 times -2 times e to the 0. So that comes out to be -2, which is a negative number. So I have negative values all in here. So the second derivative is negative everywhere there. And then finally, what is p double prime of 8? That'll be equal to 9 times 6 times e to the -8. So I get 54 over e to the 8, which is a positive number. So I believe our sign chart is complete. Next thing we're asked for is the inflection points. So by definition, inflection points happen where the second derivative goes from positive to negative or negative to positive. Or equivalently, where P goes from concave up to concave down, or vice versa. So I have inflection points where? So one of them is at x equals -1 because my concavity goes from upward to downward. And then I have another at 2 because my concavity goes from downward to upward. So sign chart is complete. So is my identification of those inflection points. So part B, we are given that this is a critical number. So x equals radical 5 minus 1 over 2. So what does it mean? What is a critical number? By definition of what a critical number is, that's where the first derivative is equal to 0. So I know that if I evaluate the first derivative at radical 5 minus 1 over 2, I get a value of 0. So now we're being asked, does P have a local minimum, local maximum, or neither at this point? So this is where the second derivative test can be used. Basically, if I have a place where the first derivative is equal to 0, that's what a critical number is. The second derivative can tell me what kind of critical point that is. So I'm going to evaluate the second derivative at radical 5 minus 1 over 2. So that's equal to radical 5 minus 1 over 2 plus 1 times radical 5 minus 1 over 2 minus 2 times e to the negative radical 5 minus 1 over 2. So one thing I want to point out here is I don't really care about approximating this very closely. All I really care about is whether it's positive, negative, or 0. So because of that, I'm just going to look at each one of these factors and try to figure out if it's positive or negative. So let's go a step further here with the simplification. We can find common denominators. So radical 5 minus 1 plus 2 all over 2 times radical 5 minus 1 minus 4 all over 2 times e to the negative radical 5 minus 1 over 2. Let's see if we can figure out what the signs of each one of these three factors is. So if this is radical 5 plus 1 over 2, and this is radical 5 minus 5 over 2, and this is e to the negative, yeah, I can't simplify this one very much. Radical 5 plus 1 is going to be a positive number. Dividing that by another positive number, that's going to make this positive. What about this? 5 is bigger than radical 5, so I believe this middle factor will be negative. And then, like I said in part A positive number e raised to any power will be positive, so this is positive. So I believe I have a second derivative, which is negative. So that tells me that I have a function that comes to a horizontal tangent line, but is concave down. So that means I have a local maximum at this critical number. All right, moving on to part C. Okay, so we're given a specific point, 12 over e squared, and we're asked to find the equation of a tangent line. So I think it's usually a good place to start to go to point slope form. So y minus y1 equals the slope times x minus x1. And I have three pieces of data that I have to fill in here. So I think the y1 and the x1 are going to come from the coordinates of this point. So y minus 12e over e squared equals the slope times x minus x1. So x1 is the x coordinate at that point, so 2. The slope is going to come from the value of the first derivative at that point, which we're given here. It's negative 5 over e squared. So let's simplify a little bit to get it back to slope-intercept form. So negative 5 over e squared x plus 10 over e squared. So I get y equals negative 5 over e squared x plus 22 over e squared. So here's my equation for the tangent line at this point. But now we're asked, does the tangent line lie above the curve, below the curve, or neither? So let's look at a very zoomed in view of what's happening at this point. So let's say this is my base point, and I know the slope of a tangent line is -5/e². That's a negative number. So let's say our tangent line looks like this. So we want to know if it's concave up or concave down. So basically, it's either going to look like this: concave up or concave down. I guess it could be neither, but concave up will look like this. Concave down will look like this. So that's another kind of equivalency you can rely on, is that the tangent line lying above the curve, that happens when your function is concave up at that point. And if your if your function is concave down, that means that the tangent line lies, sorry, the curve lies below the tangent line in those points. So we're being asked what happens at x equals 2. So we could evaluate this derivative, the second derivative. So since we're being asked about concavity, well, we're not really being asked about concavity, but hopefully I've convinced you that the thing we're asked about can be looked at as concavity. So I want to know what p double prime of 2 is. So we can evaluate this second derivative at that point, or we could remind ourselves that we already found out that p double prime of 2 is equal to 0. So we're actually looking at an inflection point, specifically the point where this function goes from concave down to concave up. So we're not looking at either one of these. We're basically looking at the combination of the two. So our function basically goes from concave down to concave up. So the correct answer for this question then would be neither, because we're not looking at a place where the concavity is either positive or negative. We're looking at a place where the concavity changes.